Welcome to Precalculus Chapter 1 Graphical Numerical Algebraic Review. So that's the book that you will use if you're in Precalculus, honors Precalculus in the class. And it's not universal, so I don't even know why I'm saying this. Anyways, we will be doing the review of Chapter 1, which is analysis of functions. That's probably not what it's called. It's probably called functions and their parts or something. But it's analysis of functions. Right, we'll do 1.2 through 1.6 because 1.1 is a joke, and it's so obvious, right? I didn't do 1.1 because it was such a joke. It's just linear regression and word problems. The problems on 1.6 are much more interesting. They're better, right? Anyways, we will be doing things to look. We will be starting right now. So things to look out for in a graph. It's called. I don't know what it's called because I haven't really looked at a book. It's called the golden box or whatever. But these are all things you should look for in a graph: domain, range, discontinuity, which includes asymptote, increasing or decreasing, lower bound, upper bound, or if it's just bounded, right? Maximum or minimum. So local extrema, so local maximum or minimum, global maximum or minimum, and end behavior, right? So we're going to look at all these features. We're going to put them into f of x plus 3x minus 5. So what's the domain of this f of x minus 3x minus 5 over x plus 2? We can use a graph because it's allowed, right? I'm just gonna draw the graph right now here. So this is our graph, right? And then it's going to have a horizontal asymptote at 3, so it's gonna look something like it's gonna look something like this, right? Like this, right there. That's what it's gonna look like. This is what the graph's gonna look like. So this is the graph of 3x minus 5x plus 2. So what do you notice? Well, the domain is discontinuous. So domain is discontinuous at x equals minus 2, because then that'll be equal to 0, right? So x equals minus 2 is where the domain cannot be. So the discontinuity is the vertical asymptote is, oh god, I'm sorry, is x equals 2. It is x equals minus 2, right? Range, where can y not be? Well, the y can't be, this is equal to 3, right? This is equal to 3, because it 3x over x, I'll tell you later. Y cannot be 3, right? Otherwise, x is all real numbers, and y is all real numbers, right? X and y just can't be this. So the horizontal asymptote you can see in the graph right now is 3, right? You can do these graphically, you really can, but you have to show some kind of work. So this is the work that I will show. So x plus 2 is equal to 0, x equals negative 2, right? And then you can just figure out this horizontal asymptotes because 3x divided by x is 3, right? So increasing or decreasing? Well, looking at this graph, it looks like it's decreasing the whole time. But we can't say that it's decreasing at x equals negative 2 because it's an asymptote. There's no value in it. So it's actually decreasing, decreasing, negative infinity to 2, to negative 2, and then negative 2 to infinity. And I forgot to put the u. I should put the u right there. I'm sorry. There's the u. Okay. So local bound, upper bound, and boundedness. Well, this isn't bounded. You could tell. Maximum or minimum. Local extreme. There's no local extrema. Maximum or minimum. Absolute extrema. Well, absolute max is infinity. Infinity is max, and negative infinity is minimum, and it occurs at minus 2, right? So we could write in limit notation, which I will write it later, not now. So the end behavior is, well, they all kind of just go flat to 3 because 3 is the horizontal asymptote, so they'll go flat, level off to 3. So end behavior is limit x approaches infinity is 3, and limit x approaches negative infinity is 3 as well, right? Okay, so is this page 2? Yeah, this is page 2. So this is how to find asymptotes. Asymptotes are those dotted lines that I wrote down, right? So for the horizontal asymptotes, it's a little confusing that I said, right? So we're just gonna work through these examples if you want to read this off. If the degree on the top is higher than the degree on the bottom, for example, this degree is 1, but this degree is only 1/2, right? X to the 1/2. Then there's no horizontal asymptote, right? If they're equal, then you take the coefficients. So you take the number before the the number before the x squared or the x or the x cubed or whatever it is, right? You ignore all this, so -5, -6, no one cares, right? And then you take 3 and 2 and you divide them together. So horizontal asymptote is 3/2, right? If it was 6 or something, it would be 6/2. If this was 6, it would be 1/2, right? The 6/2 is 3, so that's equal to 3/2. But you can't just say 3/2; you will get it wrong. The horizontal asymptote is actually y equals 3/2, right? And then what if it's lower like this, then it's automatically y equals 0. So this is y equals 0, right? Vertical asymptote, well, set the bottom equal to 0 and solve. So you set this bottom 2x minus 6, and you set it equal to 0. So you solve it, you should get x is equal to 3. And that is your vertical asymptote right there. Right? For this one, there's two vertical asymptotes. The graph actually goes something like this, right? It looks like a sad face. The graph goes something like this because there's two vertical asymptotes, one here and one here, and you could solve it algebraically because x squared minus 1 is just x plus 1, x minus 1. So the two vertical asymptotes are plus minus 1. And in this one, 2 square root of x minus 10 is equal to 0. So 2 square root of x minus 10 is equal to 0. So you add 10 together, you'll get 2 square root of x is equal to 10. Square root of x is equal to 5. And then x is equal to 5 squared, which is 25. So 25 is your asymptote. X equals 25 is your asymptote, so it's pretty far. Page 3, determine the features of f of x equal to 4 over 1 plus e to the negative 2x. I kind of regret doing this because this is a hard function. You know, let's make it a little. I'm gonna make it a little easier because I don't want to do this. Let's make it easy, right? So the logistic function looks something like this, right? This is the logistic function. It looks something like this, right? But it's 4. Since it's 4, our top has to be 4 and our bottom is 0, right? So our horizontal asymptotes are 0 to 4, are 0 and 4, so y equals 0 and 4, right? Our vertical asymptotes, well, we don't have them, none. Our domain is infinity, our domain is all real numbers. And our range is actually only between 0 to 4. Yeah, our range is only between 0 to 4. So, and it's increasing on the whole thing, right? It's increasing slowly, and then quickly, and then slowly, but it's increasing on the whole thing. So, increasing, lower bound, upper bound, or bounded. This is bounded. The reason why it's bounded is because there's no maximum value and there's no minimum value. However, for the max and min, there is no local extrema. There is no local maximum or local minimum because it's not local, right? You have to get all the way to infinity. If you have to get all the way to infinity, you have to go all the way to London. If you have to go all the way to London to experience your favorite dish, you're not gonna call it a local favorite dish. You're gonna call it a global favorite dish or my absolute favorite dish, right? If you have to go all the way to Stockholm, Sweden, to work on a project, you're not going to say it's a local project, it's a community project. You're not going to say that. It's a global. It's a global project. It's a overseas project, right? So if you go all the way to infinity to get your local, it's not a local. So there's no local maximum or minimum. However, there is an absolute um, maximum or minimum, and the absolute maximum is 4 and the absolute minimum is 0. And behavior, well, we have ourselves, you know what, I forgot to use limit notation on here, I'm really sorry. We have ourselves limit as x approaches infinity, so limit, so as it approaches, as we go infinity, is equal to 4, and then limit as x approaches negative infinity is equal to is equal to 0, just 0. So there you go. I want to do this, but I don't want to do this at the same time. Okay, let's do it. Okay, so domain. What's the domain? Well, the domain is, it can really be anything except when you make the inside equal to like less than 0. So 3x minus 1 can't be, has to be less than, has to be more than or equal to 0. So 3x has to be more than or equal to 1, and then x has to be more than or equal to 1/3. Right? X has to be more than or equal to 1/3. So then that's the domain. But we have x plus 2 right here. X can't be equal to -2 as well. But -2 is smaller than 1/3, so we don't really care, right? But x is x minus 6. This x minus 6 is equal to, it's 6 to make it equal to 0. So we actually do care about the x is not equal to 6. So our interval notation will actually be 1. No, I'm sorry. Our interval notation will actually be the domain is square bracket 1/3 to 6 u 6 to infinity, and that's our domain, right? Our range. This is a tricky situation. I know that the range in some of the quizzes were messed up. It was like 0.34 and minus 0.349 or something. But the range in this function, let me actually graph it somewhere, because I actually don't know the graph of this function because it's really hard to visualize these types of functions. Okay, the domain is okay, so it's actually pretty chill function. The function is like this. It is like, wait, let me go back to x equals 5. Function is something like this. Yeah, it's something like this with x equals 3 is equal to 0. So the range is negative infinity to infinity, and that's the range, right? No, it's not like that. I'm sorry. It's something like this, right? Discontinuity, asymptote. Well, we already figured out the asymptote, -2 and 6, and the there's no well, no, there is a horizontal asymptote. The horizontal asymptote is just x equals 1/3. No, the horizontal asymptote is just x equals 0, because the top has degree 1/2 and the bottom has degree 2. So yeah. Lower bound, upper bound, or bounded. It's not bounded. Maximum or minimum? No maximum or minimum. Local maximum. You could say that the local maximum is right here. This is one of the local maximums, which is at 1/3, 0. That's a local maximum right there. But there's no local minimum. Absolute maximum is infinity. Absolute minimum is negative infinity. And behavior, limit as x approaches negative infinity. It doesn't approach negative infinity. So the end behavior for the left is just going to be 1/3 0. It's just going to be 0. And then the end behavior for the right is limit as x approaches infinity is 0. So there you go. 12 basic functions. Oh god, I've already been 15 minutes into here. 12 basic functions and transformations. So these are some of them that you should already know. You could just stare at this page and try to get all these domain and range, but I don't recommend it because it's not gonna be fun for you to get all of these domain and range. But here are the ones that you should already know, and here are the new ones, right? So I think on the next slide, I have how to remember the function, but you should already know these. Exponential, we got the identity or the regular function, the linear function, right? The quadratic function, the um, absolute value functions, and then you got all of these, which is, I don't like all of these. Okay. How do you remember the harder functions? Well, if you want to remember, if you want to have a strategy to sketch these functions, if you want to have the strategy to sketch these functions, you have to know what they do first, right? So if you don't know what ln of x do, um, you're kind of in trouble. But just plug you could just plug in the calculator. Ln of x is log e of x if you have those old calculators that don't say ln. But you can just plug these into a calculator and you'll know. The great values that I recommend you plugging in is 0 and 1 because they say a lot about the graph, right? So for example, ln of x, 0, undefined, right? Ln of 0 can't be defined, so you gotta check what it does, right? So you want to plug in x equals 1 and you'll say that it's 0. X equals 1, it's 0. And then you might try a lower function like x equals 1 half. What's x equals 1 half? It's 1 half times 1. Oh, no, what am I saying? X equals 1 half. It's 1 half times 1, so then it will become ln of 1 half, which is ln of 2 to the negative 1. So you'll get negative ln of 2, which is like 0.693 or something, right? No, minus 0.693. I think minus 0 point something, right? So ln of x, you plug in 0 and 1, you'll get really nice numbers. If you want a curve sketch, you have to ask yourself, can the range be negative? Because some of these functions, a lot of these functions, the range can be negative. For example, e to the x, and square root of x, right? Range can be negative. Domain, can that be 0? Well, 1 over x can't be 0. Ln of x can't be 0. What else can't be 0? I think that's it. There might be more. If you check out the functions over there, you can see that the domain can be 0 for some of these functions. Does it increase really, really fast, or does it increase really, really slow? And just model the functions increase and decrease over time, right? Because for example, cosine, well, it increases and decreases at a periodic rate, but e to the x, it increases really, really fast. But then we have x cubed. That increases fast, and then it slows down a little bit in the middle, and then it increases fast again, right? So it's like the hare and the tortoise. If it's trig, if it's sine or cosine, it means it's a loop, right? So that brings me to the next. Oh god, okay, blank page. This brings me to the next point. This brings me to the next point. Cosine and sine difference. What are the differences between cosine and sine? Well, the sine. Just look at the 0, right? So cosine of 0 is 1, but sine of 0 is 0. That's all you really have to remember. Then you can draw the graphs with ease, because cosine is just cosine is just like a little bit of a nudge of sine, right? You could see they're really similar to each other. They're pretty much the same thing, but one's just a little translation of the other, right? So you can actually get sine of x, and then you can put a transformation to it, and then you'll get the exact same function as cosine. In this case, it'd be sine of x minus 1, no, sine of x plus 1 half inside. No, plus pi over 2 will be the cosine function. So this is basically, well, you don't really need to even remember the negatives. Just cosine of 0 is 1 and sine of 0 is 0. Cosine starts at the top and sine starts at the middle, right? The transformations, we're going to go to the transformations now. The transformations is a little bit more, it's where a lot of people struggle in the word transformation. We have f of x is equal to, we're going to go through every transformation. So f of x equal to x squared, and now we want to substitute the x for x plus 2, right? X plus 2, what will happen to the function if we have x plus 2 squared instead of x squared? Well, notice that x plus 2 is equal to 0 when x is equal to negative 2. We're just adding 2 into the function, right? This is not the same as x squared plus 2. If it's x squared plus 2, the function can never be 0. But in this case, the function can be 0 because we have x plus 2, right? If it's x squared plus 2, it's just a shift of 2 up. But if it's x plus 2, the whole squared, then it will be x equals minus 2, it will be 0. So we just shift the minimum point of the function to minus 2. So as a result of shifting the minimum point of function from 0 to minus 2, you shifted the whole function from 0 to minus 2. Yeah, you played yourself. You played yourself hard. But it's math. And you shift the whole function to the minus 2, right? If you expand this, it will be really messy. But if you contract it like this, it will be really nice. You'll know that it's just a shift at minus 2. In the test, I don't know how hard the test is going to be. It might give you x squared plus 6x plus 9. And you're going to have to tell what shift of x squared it is, right? What's the shift? So you'll have to deduce that x squared plus 6x plus 9 is just x plus 3 squared, and then it'll be an easy minus 3, right? It'll be a shift to the left of minus 3, a shift to the left of 3. So this will be shift to the left of 2, right? Next we have g of x is equal to e to the x, and g of x is equal to e to the x minus 5. This time we have a minus 5, right? So we observe that the regular e to the x, when you put x equals 0, you get g of x is equal to 1, right? So x equals 0, g of x equal to 1. I put it right there, right? But in this one, if you want g of x is to be equal to 1, you have to put in x equals 5. So as a consequence of that, you have to shift the whole function to the right by 5, right? I have to warn you again that this is a different thing than this. They're not the same thing, right? It's kind of like this, right? So e to the x minus 5, you will lower the thing by 5, and then you'll get this same function e to the x, but just shift it down by 5. So then 0 will get you negative 4 instead. But this e to the x minus 5 is a 5 shift to the right, because x minus 5 is equal to 0, x equals to 5, when when g of x is equal to 1. So as a consequence, g of x is moved to the right by 5. So we have our next lemma. So we have f of x is equal to absolute value of x. So f of x plus 2 is equal to absolute value of x plus 2, right? And this plus 2, if it's not inside the parentheses of f of x, if it's not inside the absolute value, the square root, the 1 over x, if it's not inside it, it's really easy. It's unimaginably easy, because then all you have to do is shift it 2 up, and that's it, right? For example, if you have 1 over x, right? 1 over x looks something like this, right? If you have 1 over x plus 1, it's just shifted up by 1. And it holds true because if you simplify this 1 to x over x, right? Since 1 is equal to x over x, right? 1 is equal to x over x. You'll get 1 plus x over x. And that's your function, right? In the horizontal asymptote, it's x over x, which is 1, right? So the horizontal asymptote moves up with it as a consequence of adding 1 to the function. So subtraction will get you the same thing. If you have absolute value of x minus 5, it'll move down by 5, right? If it's not in the parentheses of the x. So if you have if you have absolute value of x plus 3 minus 2, right? It'll be x plus 3, which means left, right? So minus 3 will get you 0 inside of the function. But 0 won't actually get you 0. It'll get you minus 2, because there's still a minus 2 at the end. So we'll shift the graph to the left by 3. To the left by 3. And then since there's a minus 2, you will move it down by 2 as well. So it'll be shift to the left by negative 3 and down by 2. Next is it's a little bit confusing. This next concept about vertical or horizontal shift. So the vertical shift is just a f of x. So this is a vertical shift. This is a vertical, no, vertical stretch, right? Vertical stretch, vertical shrink. If a is higher than 0, if a is higher than 1, then it will be called a vertical stretch. If a is lower than 1, it will be called a vertical shrink, right? Because it's obvious, right? Imagine some kids go down and grab some candy, and like you have those candy canes, but they're kind of like in a liquid state, in like a malleable state, so you can just pull them up, right? uh, or like bubble gum, or for example, right? You have these bubble gum, you have these shapes, you can just pull them up, and that's the vertical stretch, right? And the vertical shrink is, imagine you have a hydraulic press from the top, and you just push the whole function down, right? That's a vertical stretch. So the vertical stretch is like this, and then the vertical shrink is like this, right? So stretch, shrink. Right? So we're trying to get you into, shrink means we're trying to get you into the axes as fast as possible. Stretch means we're trying to get you out of the x-axis as fast as possible, right? Or like as much as possible with our vertical stretch. So this is a vertical stretch because a is higher than 2. What about horizontal? Well, horizontal stretch, horizontal translations, dilations are in the form f of ax, and our horizontal transformation, not just shrink, is 1 over a, right? And you'll understand why right here. So ln of 2x, what does ln of 2x do? It increases the function, right? It doesn't decrease the function. Why would it decrease the function? Here, if our horizontal stretch was if we had a horizontal stretch, the ln of 2x would decrease, because if you stretch this horizontally, just look, it'll be something like this, right? This would be ln of 1/2 x, let's say, for example, right? This is, it looks like it's smaller. It doesn't look like it's bigger. It actually looks like it's smaller than ln of 2x, which makes sense because 1/2 is smaller than 2. So our horizontal translations have to be made in the form of 1 over a if you want to express them as a stretch or a shrink. For example, if it's ln of 1/2 x, it will be 1 over 1/2, which is 2. Then it will be a horizontal stretch of 2, right? So if the number of a is less than 1, it's a horizontal stretch, and if the number a is greater than 1, it's a horizontal shrink. So in this case, the number of a is 2, so it's a horizontal shrink, right? Horizontal shrink. And our horizontal shrink, what factors are horizontal shrink? It's 1 over a, so 1 over 2 is just 1/2, right? Our factor of horizontal shrink is 1/2, right? We'll practice right now with these functions right here. So find the stretches and shrinks of 2 integer of x, right? It's just 2, and then this is f of x, right? This is any regular function. So 2 of f of x is just a vertical stretch of 2 and no horizontal stretch. This is our f of x right here. This is our f of whatever x, and this is our vertical stretch component. So our vertical stretch component is 3, and our horizontal stretch component, it's a horizontal stretch, first of all, because the number is less than 1. It's 1 over 1/4, which is equal to 4. Right, so we want to get away as quick as possible if it's stretched, and we want to get away from the axes as less as possible. We want to attract to the axis if it's a shrink. So 3x plus 2 squared. This is a little bit this is a little bit sus. This is a little bit hard, right? You actually have to expand the function if you want to know more about it. In this case, it will be 9x squared plus 12x plus 4, right? And you have to complete the square. 9 times x squared plus 12 over 9x plus 4, and then you have to do all the different types of math. So you've already technically obtained what you wanted to obtain by doing this, right? So you could say this as a vertical stretch of 9, which I don't recommend you do. I recommend you say it's a horizontal string of 1/3. Because this, if you just look at this function, you have 3x and then you'll have the square. Since it's in the parentheses, it's f of ax. So the 3 is a horizontal transformation. You'll put the 3 into the a, and then you'll get 1/3. Right? Horizontal string of 1/3. However, you could modify this equation so that it could be a vertical stretch of 9. Right? So in this case, a vertical stretch of 9 is equal to a horizontal stretch of 1/3. This is different. This is pretty much, this is really hard, actually. First of all, you want to simplify the bottom, because you can see there's 2, right? 2 and 2. So I'm just going to put the 2 out, and now 1 e to the 1 e to the negative 3/4 x, right? So now the bottom's nice and dandy. We have 3 on top. So what's our vertical stretch in here? Well, our basic function is 1 over 1 plus 1 e to the negative x. We don't have to have the 1 here, but I'm just illustrating. So we have this 1 on top. 1 times 3 is 3, right? So we can just put the 3 out here, and then we can erase this, multiply by 1, right? And then this 2 at the bottom, it's just the denominator, it's just a factor. So it'll be 3 over 2. It'll be 3 over 2 multiplied by 1 over 1 plus e to the negative 3/4x. So our vertical stretch is 3 over 2, and our horizontal, is it a horizontal stretch or horizontal string? Well, 3/4 is negative 3/4. We're not trying to incorporate the negative. So whenever you say it's a horizontal stretch, you don't have to put the negative. You don't have to say negative 4/3 horizontal stretch, because that would just imply that it's a reflection and a horizontal stretch. So our horizontal stretch is just 1 over 3/4. 1 over 3/4. I'm not sure if this is even visible, which is equal to 4 over 3, and that's our horizontal stretch. So next up, we have reflections, right? Reflections are a little weird. I'm just gonna try to get the intuitivity out of you. Fx equals 3x plus 2, negative fx equals negative 3x plus 2. This negative is a unavoidable thing, right? This is unavoidable. So if you do 3x, you'll get, if you do 3 times 2, right, for minus 3x plus 2, you do 3 times 2 plus 2, you'll get 8. You do negative, if you do 3 times 2 plus 2, but it's negative 3x plus 2, you'll get negative 8. Anything that you do on the top is going to be negative. Anything you do on the top is going to be negative. Let's do some of it on the graph, right? Let's say it's this point, right? This point is f of x. Negative f of x is here. This point's f of x. Negative f of x here. This point of f of x, negative f of x right here. This point is this point is f of x. Negative f of x right here, right? So I don't know. This function might look like that. But whatever you do, it's just going to be the opposite. With respect to the y-axis. So with respect to the x-axis, I mean x-axis. Therefore, the function is just a reflection upon the x-axis, right? And I'm pretty sure you're allowed your notes and you're allowed your book, but you really should remember this because you have 50 minutes to do 20 questions. So it's a reflection on the x-axis. That's the negative f of x. But what about this, right? G of x is equal to integer of x. G of negative x is equal to integer negative x. So if we put g of x is equal to, well, now I'm going to draw the integer function right now. It's probably not the best example to illustrate, right? This is our integer function, and it's going to be something like this. Yeah, just know that it does this, right? Okay. Anyways, so what's going to happen if we put negative x? If we put negative 0 in, nothing's gonna happen. If we put negative 0.5 in, right? So x, now we have 0.5 is negative 0.5. So if we put our negative 0.5 in, what's the greatest integer of negative 0.5? It's negative 1, right? So 0.5 will be negative 1. If we put, let's say, negative 3.2, so we have x at 3.2, but we have negative 3.2. What's the greatest integer? It's negative 4. So negative 3.2, negative 4 is about right here. What if we put 2.8, right? So negative 2.8. Now we have negative 2.8 as our thing, and we put 2.8 in, we'll have our greatest integer is 2, right? So then you'll get this type of graph right here. You'll get this type of graph. What does this look like? It looks like an X, obviously. But what does it look like? It's a reflection on the y-axis. So whenever the negative is inside the function, if you see ln of negative x, it's a reflection on the y-axis. See, then you'll have the graph like this instead of like this, right? If you have negative ln x, it's opposite. It's this graph instead. So negative ln of x will be this graph instead, right? Because it's a reflection on the x-axis. This is a reflection on the y-axis if you have the negative inside of the function, just like the horizontal stretch. So what axis is this on? E to the negative x? It's on the y-axis. What about this? X-axis. You should be able to just look at it and see, right? This 3 minus x, see, it's the minus x is inside the parentheses, and it's not just a big fat minus at the beginning of the function. It's each thing deserves its own respect, and that constitutes to a y-axis reflection. Now this is a little bit tricky because minus x cubed can be both, right? If you take minus x cubed, if you take minus x cubed like this and you multiply it minus x, it's minus x cubed. So it can be both. It's x or y axis, right? Both the x and or the y axis. So that brings me to the next point, which is oddness and evenness, right? So what is an odd function? Well, the odd function is a function that whenever you rotate it 180 degrees about the origin, it replicates itself. It mirrors itself, right? And then functions are even whenever they mirror themselves when reflected over the x-axis. So this is the test for functions. Odd functions are like this, and even functions are like this. I recommend you write this in a note card or something because it probably will be useful. It might not though because he hasn't really thought about odd or even functions that much, but it might come on in sense. There's a faster test for functions though. There is a faster test for functions, and it's pretty useful actually. So if all the degrees are even, the number has an even degree, and it's going to be an even function. If all degrees are odd, it's an odd function, right? The negatives count as well. So 1 over x is odd, 1 over x cubed is odd, 1 over x to the 5th power is odd, right? So it would be x to the negative 1, x to the negative 3, x to the negative 5. If there is one even and one odd degree, then the function isn't even, neither is it odd, right? So x plus 1 is x plus 1, not even or odd, because 1 has a 0th degree and x has a 1 degree of 1. So which of the 12 basic functions are even, odd, or neither? I'm going to write the function now. You can spend a few seconds to try to get known of them, right? Like get used to them. So we have x cubed, we have ECX, we have 1 over x, we have absolute value of x, we have sine of x, we have cosine x. Some of these you do just have to remember. like sine and cosine, right? And then we have 1 over 1 plus e to the minus x. We have ln of x. We have integer of x. We have, what else? X cubed. And then finally we have square root of x. So I'm gonna give you 5 seconds, pause the video, try them for yourselves. Okay, so here are the answers. X is odd because it has a degree of 1. That's even because it has a degree of 2. This has varying degrees, right? The degree is a variable itself, so it's neither. This is 1 over x, so it's odd. This is even because if you look at the graph, when it's reflected over the x-axis, no, wait, I did this wrong, I'm sorry. When it's reflected over the y-axis, when it's reflected over the y-axis, I'm really sorry, I did it wrong. Y-axis, then it is the same thing, right? So that's even. Sine is odd, you just have to remember that. Cosine is even. You can look at the graph. I forgot to fix the y. I'm really sorry. I forgot to fix the y. The y would have made it clearer that this is an odd and this is an even function. This is neither. Ln of x is neither. Integer of x is neither. X cubed is odd, and square root of x is neither. Alright, so these are the odds and evens of the functions. Next page. I think I just got lazy here. Find f of g of x and g of f of x for x is equal to this and g is equal to this. F of g of x, you should already kind of know this function compensation stuff. I'm just going to do it anyway. We have f of g of x. This is f circle g of x. I used O because I was lazy. F of g of x, so we put g of x in every single thing where it says x, right? So f of g of x will be 3 times x minus 7 minus 1 over 3 times the square root of x minus 7 plus 2. And that is our f of g of x. You could obviously simplify this. You could do square root of x plus 7 minus 2, 3 squared of x minus. You could do that, but I'm not going to do that right now because this video is already 42 minutes long. Probably more boring than Mr. Christensen's videos. But what is this? Right? What is f of x? We'll have 3 times square root, and I drew a big square root there because we're going to fit this whole f of x, x minus 1, over x plus 2 minus 7. And that's our g of f of x, right? We could make the minus 7 a common factor by doing 7x plus 2, and then doing x plus 2, and then just erasing this, and then do that, and then you can combine these two together. That's also a good simplification method. You can rationalize the denominator and do all that, but I'm just not going to do it right now. There's a caution that I'm going to give you. Composed functions have the domain of its parts and its real domain. So this, let's say f of g of x. We want to put f of g of x here, right? Or g of f of x. Let's do g of f of x, right? What's the domain of g of f of x? Well, it's 2x minus 7 over 2x minus 7 minus 1, which is 2x minus 8. So the domain of this is x cannot be equal to 4. But this is a composed function. This is a not composed function. Yeah, I'm just gonna say composed function. This is a composed function. So we have to take the domain of each part as well. So what's the domain of f of x? It's all real numbers. What's the domain of g of x? X can't be equal to 1, right? So you have to say x can't be equal to 1 and x can't be equal to 4 when x belongs to the real numbers. To find an appropriate f of x and g of x for this function, sine of 2x minus 5, we'll have f of x is equal to, for the function, let's say h of x is equal to f of g of x, right? This is just to formalize things. So f of x is equal to sine x, g of x is equal to 2x plus 5 minus 5. Pretty obvious because when you put 2x minus 5 inside sine x, you'll get sine of 2x minus 5. Find an appropriate fg and h of x for the function w of x equal to fg of h f of g of h of x. equals to ln of 27x cubed. Now, first of all, when I see this 27x cubed, I see a nice number, right? 27x cubed is nice. So it'll be 3x to the third power, right there. And that's really useful, because then now we can actually have three functions, right? So our first function, f of x, is just ln of x. Our next function, g of x, is, well, we got to think about it. We have 3x cubed, right? 3x cubed. So what is the function in the inside? It's the 3x. What's the function in the outside? It's the cube. So we have to put x cubed, and then our h of x is 3x. So now we can put 3x into this. We'll get 3x cubed. And we put 3x cubed into ln x. We'll get ln of 3x cubed, which is ln of 27x cubed. Same thing. 12. Parametric equations. Okay, this review is lasting way too long. I think I'm just gonna stop here and I'll do the rest later. That's gonna be it for this part of the review. Good luck.